Pressure altitude is the altitude above sea level. The altimeter indication when QFE is set on the subscale. Altimeter indication when QNH is set. Altimeter indication when 1013 is set. So pressure altitude. Pressure altitude is always measured from standard pressure setting 1013. So correct answer is option delta. Consider this is your airport. Okay. This is your mean sea level and this is your standard pressure setting datum 1013. Now, let's say this is one aircraft which is parked on the airport. Okay. And the altimeter setting, the altimeter set, the pressure setting in the altimeter setting window is equal to QFE. Now, what is QFE? QFE is nothing but the aerodrome level pressure. What is QNH? QNH is aerodrome level pressure, which is QFE, reduced to mean sea level. That means converted to mean sea level. So that is your QNH, and this is standard pressure setting 1013. So when you set QFE in the altimeter setting window, the vertical distance shown by altimeter will be equal to 0 feet. Okay, the vertical distance shown by a altimeter will be equal to 0 feet because you are on the ground and you have set QFE in your altimeter setting window. Now let's take another aircraft which is again parked on this airport and it has put QNH in its altimeter setting window. In this case, the altimeter will indicate elevation of this airport. Now elevation is measured from mean sea level. So if you put QNH in the altimeter setting window, the vertical distance will be measured from mean sea level or QNH pressure level. Now let's consider another aircraft which is in the air. Now this aircraft has put 1013 standard pressure setting 1013 in its altimeter setting window. So the vertical distance shown by this altimeter will be from standard pressure setting 1013 pressure level. That will be called pressure altitude. Pressure altitude. Okay. So pressure altitude is nothing but altimeter indication when 1013 is put in the subscale. Which of the following cause air density to decrease? Air density to decrease. So air density is controlled by air density is controlled by three factors. First, the temperature. Second, atmospheric pressure. And the third, humidity. Right? Our density of air is controlled by three factors: temperature, humidity, and pressure. Now, increase in temperature will decrease density. The air will become thin. Okay, increase in temperature means temperature becoming warmer and warmer than ISA. So density of air will start decreasing. The air will become thinner and thinner. If temperature decreases or becomes colder than before or colder than ISA, the density of air will increase. The density of air will increase. Next, atmospheric pressure. Now, if atmospheric pressure increases, the density of air will also increase. If atmospheric pressure decreases, as it does when we go to higher altitudes, density of air will also decrease. Humidity. If air is humid, a humid air will decrease your density. A dry air will increase your density. So that means dry air is good for density. So the question, which of the following cause air density to decrease? So look at this slide. So air density will decrease under three circumstances, three conditions. When pressure decreases, when temperature increases, and when air becomes humid. So increase in humidity, yes. Increase in altitude, yes. When you go to higher altitudes, pressure decreases, therefore density also decreases. Increasing temperature, yes. So all these three parts of the answer are right. So option statement A is right. Increasing humidity, yes. Increasing altitude, yes. Decreasing temperature means temperature getting colder and colder. So that will increase your density, not decrease it. So this part of the statement is wrong. Increasing humidity, yes. Decreasing altitude. So when you come down to lower and lower altitudes, pressure increases, density increases. So this is wrong. Decreasing humidity, no. So decreasing humidity will make air more dense or denser. It will not, as opposed to decreasing its density. So statement A or option A is the right one. If QRH changes from 1013 to a new pressure 1022, what will happen to field elevation? It will increase field elevation, it will decrease field elevation, not affect field elevation, decrease QFE. So, so situation number one, let's consider this is your airport, and the mean sea level here in situation one is 1013. So the elevation of the airport will be measured from QNH, mean sea level, so it will be this much. QFE is whatever. So next, condition number two, this is your airport, same airport, but and this is the mean sea level now, and now the mean sea level is 1022, and this is your elevation of the airport. Okay, so QFE, this is QFE is nothing but aerodrome level pressure. So remember, if QNH increases from 1013 to a new value, or it decreases from 1013 to another new value. Okay, so whether it increases or decreases doesn't matter. Just remember this fact that if QNH changes by some value, then the QFE will also change by the same value. That means the relation between QNH and QFE won't change. It will not change. If QNH increases from 1013 to a new value of 1022, that is, if QNH increases by 9 millibars, QFE, whatever that is, it will also increase by 9 millibars. So, as a result, the elevation of the airport will not change. The elevation of airport only changes when there is an earthquake, okay, there is movement of tectonic plates and all that. But just the change in pressure will not change the elevation. Elevation of airport will remain fixed. Pressure changes, so therefore QNH changes. Along with it, QFE will also change. If QFE changes, QNH will also change with it. So elevation of the airport will not be affected. Next, question number 24. If QFE changes, now similar question, if QFE changes from 1013 to a new value of 1022, so what will happen to QNH? QNH will also change by that much amount. So it will increase field elevation, it will not affect QNH, it will increase QNH, it will decrease QNH. Now here QFE has increased by 9 millibars. So QFE has increased by 9 millibars. So as a result, QNH will also increase by 9 millibars. So option Charlie is the correct answer. Field elevation will not be affected. Field elevation will remain the same. It will influence QNH. It will not decrease, it will increase QNH. Next. Equivalent airspeed is calibrated airspeed corrected for adiabatic compression, indicated airspeed corrected for adiabatic compression, indicated airspeed corrected for instrument error, instrument indicated airspeed corrected for for pressure sensing error. So correct answer is option A. Equivalent airspeed is calibrated airspeed corrected for adiabatic compression. As pressure altitude increases, when climbing at constant indicated airspeed, calibrated airspeed will increase, calibrated airspeed will decrease, true airspeed will increase, true airspeed will decrease. Very important question. So I have explained this question many times in my previous video lectures. Let's consider you are climbing in this particular atmospheric layer. Okay, you are climbing in this particular atmospheric layer to higher altitudes. Now, as you go to higher and higher altitudes, atmospheric pressure, atmospheric pressure will decrease. Correct? Atmospheric pressure will decrease. Now, your airspeed indicator is nothing but a pressure instrument. Is a pressure instrument. This pressure instrument measures dynamic pressure. Measures dynamic pressure. Okay. Now, when you go to higher and higher altitudes where atmospheric pressure goes on decreasing, what will happen? The pressure available for registration by airspeed indicator will also go on decreasing. So, if atmospheric pressure surrounding your aircraft decreases, so the pressure that is registered by the airspeed indicator will also decrease. If pressure registered or processed by the airspeed indicator decreases, so the dynamic pressure that it calculates or registers will also decrease. If dynamic pressure decreases, the corresponding output, what is the output? Airspeed indicator or indicated airspeed or calibrated airspeed will also decrease by that much amount. Airspeed indicator measures dynamic pressure. This dynamic pressure is shown to us in the form of indicated airspeed or calibrated airspeed. So if one value decreases, it will be followed by a decrease in another value, right? So dynamic pressure decreases, calibrated airspeed or indicated airspeed will also decrease as we climb to higher altitudes. So we will be flying at constant true airspeed, okay, but the speed shown to you in the airspeed indicator will decrease because it's dependent on atmospheric pressure, namely dynamic pressure. So in order to prevent that from happening, if you want to prevent that from happening, what will you have to do? You will have to increase the forward speed of your aircraft. You will have to increase the true airspeed of your aircraft. When you increase the true airspeed of your aircraft, what will happen? The dynamic pressure will increase. This dynamic pressure, okay, dynamic pressure will increase. This increase in dynamic pressure will compensate for any fall in static pressure as you climb to higher altitudes, right? So you will increase your true airspeed to that extent, up to that amount, till when, as much as or to the point where calibrated airspeed will stop falling. So if calibrated airspeed stop falling at a particular true airspeed, you're going to maintain that true airspeed. Okay, so that increase in dynamic pressure will compensate for the decrease in static pressure around you. So always, if you want to maintain a constant calibrated airspeed as you climb to higher altitudes, increase the forward speed of your aircraft, the true airspeed of your aircraft. So the correct answer is true airspeed will increase. Okay, if you increase the true airspeed, dynamic pressure will increase. So dynamic pressure increases, so the corresponding representation, which is your indicated airspeed or calibrated airspeed, will also increase. As pressure altitude increases when climbing at constant Mach number, what will happen to CAS? What will happen to TAS? Okay, so again, let's say you're climbing in a particular air mass. Now, when you climb to higher altitudes, decreases. Atmospheric temperature decreases. Now, here in this question, it's stated that you're climbing at constant Mach number. That means the Mach number at lower levels is, let's say, 1, or let's say it's zero point 0.8. So as you go to higher altitudes, you are maintaining that constant Mach number of zero point 0.8 there as well. Okay, you are maintaining that constant Mach number. So what will happen? Now Mach number is equal to true airspeed divided by local speed of sound. Now first things first, as you climb to higher altitudes, atmospheric pressure decreases. This decrease in atmospheric pressure will impact or influence your airspeed reading. So if atmospheric pressure decreases, dynamic pressure registered will also decrease, and therefore if dynamic pressure decreases, your indicated airspeed will also decrease. So calibrated airspeed will increase? No. Calibrated airspeed will decrease, then remain constant? No. As you go to higher and higher altitudes, atmospheric pressure keeps falling and falling. The calibrated airspeed will is expected to continuously fall. It won't remain constant at any level in the atmosphere. So Bravo is also eliminated. Now we are left with TAS, and TAS will increase, TAS will decrease, then remain constant. Now let's say you are at 5,000 feet. You are at 5,000 feet here. At 5,000 feet, atmospheric temperature, ISA temperature is 5 degrees Celsius. So local speed of sound at uh, 5,000 feet will be 39.17 square root of temperature in Kelvin. Okay, so convert this 5 Celsius into Kelvin. So 5 plus 273 is 278. So 39 square root of 278 is 116.67. So approximately 17. Okay, and multiply that by 39.17, you get a value of 653. So local speed of sound at 5,000 feet where temperature is 5 degrees Celsius is 653 knots. So true airspeed will be equal to Mach number multiplied by local speed of sound, cross multiply. So 0.8 multiplied by 653, that is equal to 522. So task is 522. Now let's go to a higher altitude. Let's go to 10,000 feet, where the Mach number is still the same, but temperature at 10,000 feet will be equal to 15 minus 20, that is minus 5 degrees Celsius. So minus 5 plus 273 is 268 Kelvin. Local speed of sound at 10,000 feet is 39.17 square root of 268. Square root of 268 is whatever, 16.37 multiplied by 39.17 is 641 knots. Okay. Now, TAS at 10,000 feet in this conditions, under this conditions will be Mach number zero point 0.8 into local speed of sound 641. That is equal to 513 knots. 513 knots. So 522 has become 513. Okay, 522 has become 513. So that means true airspeed has decreased. Correct. This is the Demonstration of proof of that. So the correct answer here will be delta. TAS will decrease, then remain constant. Why? Why will it remain constant? Because after a certain altitude, after or beyond 36,000 feet, ISA conditions state that atmospheric temperature stops falling. That means it remains constant at minus 56.5 degrees Celsius. So if atmospheric temperature beyond 36,000 feet stays constant, the local speed of sound will also remain constant. So if Mach number is constant, local speed of sound is constant, therefore true airspeed will also remain the same. So therefore delta is the right answer. Next, question 28. As pressure altitude increases, temperature decreases, yes. Temperature increases, no. Temperature increases then remains constant, no. Temperature decreases then remains constant, yes. So now both options alpha and delta are the right ones, but delta is the more appropriate one because it is more specific. Temperature decreases as you go to higher altitudes, correct. Second point, beyond 36,000 feet, atmospheric temperature remains constant. So that's why we have selected delta. Question 29. When descending at constant calibrated airspeed, dynamic pressure increases, dynamic pressure decreases. Now, if you are descending at constant calibrated airspeed, that means, in other words, you can say you are descending at constant dynamic pressure. Like I explained before, calibrated airspeed is nothing but dynamic pressure. So, dynamic pressure cannot increase nor can it decrease. Dynamic pressure remains constant and decreases. Dynamic pressure remains constant. So, option delta is the right answer. Okay. So constant speed, calibrated airspeed or constant indicated airspeed is nothing but constant dynamic pressure. At a fixed pressure altitude, so that means you are flying at a straighter level at a particular altitude, an increase in temperature will decrease density, yes. Increase density altitude, yes. Decrease density altitude, no. Not affect density altitude, wrong. Increase density, no, it will decrease it. So option alpha is the right one. Increase in temperature will decrease air density. If air density decreases, density altitude will increase. It will be more than pressure altitude, meaning you are flying at 5,000 feet. But since density of air at 5,000 feet is much less than expected, much less than what it should be, so your aircraft will deliver performance according to the density, according to the lesser density, which is at 5,000 feet, and this less density is normally expected to be found at altitudes more than 5,000 feet, let's say. So your aircraft will deliver a performance uh, which is uh, which is equal to performance delivered at higher altitudes where that low density is normally found. So therefore we say density altitude will increase. This concludes our lecture. I hope you have understood all the questions that I have answered in this video lecture. If you have any doubts or questions, let me know in the comment box. I request you all to share this channel with your friends. Subscribe to this channel if you haven't yet, and hit the like button if you have liked this video lecture. Don't miss my next lecture. I will come up with some new questions and we will solve them.